Good evening. Now this is going to be my short one. We're going to talk tonight about the universal law of gravitation that was formulated by Sir Isaac Newton. Sir Isaac Newton was a brilliant man, but he still understood that it was because of the people who came before him that he was able to make the observations and the conclusions that he did. He's famous for saying, "If I have seen farther than others, it is because I have stood on the shoulders of giants." He lived in the same century as Kepler, but was at the end of the 17th century. Johannes Kepler was in the early to mid 17th century. And so Newton certainly knew about Kepler's three laws of planetary motion, and a lot of his work in formulating his theory of gravity came from the novel ideas of Kepler that the orbits were ellipses and that the sun was one of the two focal points. Newton's universal law of gravitation is basically known because it describes gravity, which was first formulated by Galileo. The word was coined by Galileo to talk about the force that caused things to fall to the earth. And he discovered, Isaac Newton did, that this action at a distance was actually the cause of the motion of the planets around the sun. He was very much enthralled with the Earth's gravitational force and saw that the same force that caused an apple to fall from a tree was the one and exact same thing that kept the moon in orbit around the Earth. Gravity is the force that results in a centripetal-like acceleration of the planets. And even though our orbits are ellipses in our solar system, as the gravity of Earth causes an apple to fall from a tree and the moon to orbit Earth, the sun also exerts a gravitational force that causes the orbits of the planets around it. The orbital paths of that we are used to with generally circular motion are true circles. And then we talked about ellipses. But Newton was able to extend Kepler's first law to find that there were other orbits possible. These orbits could be ellipses, which are bound, closed circles and flattened circles, or they could also be unbounded parabolas and unbounded hyperbolas. Now, you've heard of these terms in mathematics and also in our discussion of graphing values, but here is what we're talking about. When a comet, for example, is way, way far beyond Pluto and then comes in and takes a very, very long time, hundreds of years or thousands of years to come into the solar system near the sun, it may have an unbounded hyperbolic orbit because it's far away from the focus, and it is so far away from the focus that it's actually looking so flat that it seems like a straight line. You could also have a Kuiper belt object, for example, which is what a lot of different orbital paths are bringing around the solar system, that would form an unbounded parabolic orbit. The orbits of the planets are bound orbits, and those are elliptical. And then also down here in the cone, you see that a circle, which is the simplest of these, is something that can also be derived through conic sections. If you're taking calculus right now and you're working in conic sections, you'll know exactly what I mean. But this was a less well-known contribution that Newton made to the ideas of orbiting objects. Newton's universal law of gravitation, as stated, says that between any two objects in the universe, there is an attractive force, and that force has a magnitude that is directly proportional to the mass of each of the objects and inversely proportional to the square of the distance between their centers of mass. Here, stated in mathematical form, we see that the force of gravity between any two objects in the universe is directly proportional, meaning that the gravitational constant G is the constant of proportionality, directly proportional to the product of the masses that are involved, two at a time, and inversely proportional to the square of the distance between their centers of mass. Let's take a look at how we completed Newton's universal law of gravitation by the work that Cavendish did, that is in your book, that I want you to make sure you read. Cavendish was the person, remember, who performed experiments, very, very careful experiments, to determine the proportionality constant for Newton's law of gravity. And he came up with the value of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That allowed us to do many, many different things with Newton's law. And we will be working tomorrow to show you how we can actually derive other equations for orbital velocity, orbital period, lots of different kinds of things from universal gravitation. Here, what we're looking at now is the complete version of Newton's universal law of gravitation, where we know the value of G. So that means that we're ready to try calculations. The calculations that we can do with Newton's universal law of gravitation are very, very many and different. The most obvious one is when you're looking for the gravitational force between them, and that should be pretty simple. So I thought I would take a look at one where you're looking for how far apart their centers of mass are. That would be the R in the denominator. So let's take a look at this problem. Mars has a mass of about 6.4 times 10 to the 23rd kilograms, and its moon Phobos has a mass of about 9.6 times 10 to the 15th kilograms. If the gravitational force between them is 4.6 times 10 to the 15 newtons, how far apart are Mars and Phobos? Mars has two moons, Phobos and Deimos, and Mars is considered to be the god of war. He was a very fearsome god. And the two moons of Mars, Phobos and Deimos, means fear and destruction. And so they are very aptly named for moons of Mars. Alright, so let's take a look at how we're going to solve for the orbital radius, R. Remember that is going to be extremely important to get the right value for that distance. It's the distance between the two centers of mass. So we start with F equals gmm over r squared. Notice that I always call the central body mass capital M and the orbiting mass little m. That helps me keep straight what is going to be canceling if I ever cancel an m. So what I see here is that I'm trying to solve for r. So my goal is to get r squared alone on one side. Since it's in the denominator on the right, I'm going to multiply both sides of the equation by r squared, and while I'm at it, I'm going to divide both sides by f. So now I've simplified the problem to r squared equals g mm over f. Putting in my numbers, I will come out with the value of 9.4 times 10 to the 6th meters. So with that in front of us, let's get your calculator and make sure that you're able to get through these big numbers without any kind of problem. All right, so we are looking at the middle equation right here, r squared equals gmm over f. So I'm going to put in g first, 6.67 times 10 to the negative 11. You can do that with your caret sign. I would suggest you do that. Or you can do the EE. So I've got that in there. And I can just continue right ahead and multiply by the mass of Mars, which is 6.4 times 10 to the 23rd. Now I haven't put any commas in or parentheses or anything in, okay? And Phobos has a mass of 9.6 times 10 to the 15th. So I'm going to continue to multiply by 9.6 times 10 to the 15. Now I have to enter because I'm at the end of my numerator. And I'm looking at 4.098048 e to the 29th. Hopefully you're getting the same thing. Now I'm going to divide by, let's take a look, F, the force which has been given to us, okay? And that is going to be 4.6 times 10 to the 15th. Now in the denominator I have to put a parentheses before I write that number. So I have a parentheses in there, and you can insert it if you forget. But the parentheses has to go in first, and then I have 4.6 times 10 to the 15th. If I was squaring something in the denominator, I would put in 2 parentheses to begin. Okay? So now I'm dividing that by 4.6 times 10 to the 15th, and I'm looking at 8.9088 times 10 to the 13th. Now, what I have to understand is that I just solved for r squared. So I'm going to take the square root, second answer, and I'm looking at right now at 9438643.97. And the answer that's right in front of us is 9.4 times 10 to the 6th meters. So that is a sample problem from Newton's universal law of gravitation. There's a lot more we can do, and that's going to be for tomorrow. So let's just review that the universal law of gravitation says that the force of gravity between any two objects in the universe is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers of mass. We're going to also remind ourselves that Newton is responsible for developing different types of orbits that could be made possible and have actually been verified. Objects that are bounded are going to follow elliptical shapes. We can also send orbits of artificial satellites as circles. And then we will also have unbounded orbits in the shapes of parabolas or hyperbolas, depending on how far out in the solar system they're coming from. Okay? Now tomorrow we're going to derive some more equations that will allow us to apply universal gravitation to many, many different topics. Among them, we're going to be taking a look at Newton's version of Kepler's third law, and we're going to find its most general form for circular orbits. I'll show you how we're going to be able to derive that. And then that will allow us a lot of freedom to describe what the orbital period is of the two objects, what the distance between them is, and the mass of the central body. In addition to that, we're going to be able to derive escape velocity equations, orbital velocity equations, how much g would be on any given planet, and the period and average orbital radius of any orbiting body. Okay? So we'll see you tomorrow. Bye-bye.